On the night of May 16, 1943, a Royal Air Force crew was asked to do something that sounded less like bombing and more like a controlled crash. They had to take a 4-engine Lancaster down to roughly 60 feet above a black reservoir. They had to hold a precise speed. They had to fly straight toward a massive German dam while light anti-aircraft guns fired almost horizontally at them. And under the belly of the aircraft hung a steel cylinder weighing more than 4 tons, already spinning backward before release. Then at just the right distance, the bomb aimer had to let it go. The weapon was not supposed to fall cleanly into the water. It was supposed to hit the surface, leap back into the air, strike again, and keep skipping forward like an impossibly heavy stone. The bounces were meant to carry it over defensive nets that would stop a normal torpedo. If everything worked, the cylinder would reach the dam, sink beside the wall, and explode underwater where the reservoir itself could help drive the blast into the structure. That was the theory. But the theory had a brutal condition. It would work only if a bomber built for high-altitude war could be flown in darkness at a height where a small error was no longer an error. It was a collision. And in May 1943, the Royal Air Force was about to discover whether mathematics could survive contact with fear. The targets were 3 great dams in western Germany, the Möhne, the Eder, and the Sorpe. They helped regulate water across the Ruhr, the industrial region that fed coal, steel, transport, and armaments into the German war economy. Their value was not simply that they could generate power. Reservoir water also supported industry, canals, and the processes that kept factories working. For British planners, the dams represented a tempting concentration of infrastructure. Damage the right structure, and the effect might spread well beyond the concrete itself. The problem was that the dams were built to resist enormous pressure every day. A gravity dam like the Möhne survived because its sheer mass pushed back against the reservoir. Its wall was not a thin target waiting for a direct hit. It was a vast wedge of masonry and concrete, broad at the base and narrow at the crest. A conventional bomb dropped from high altitude faced 2 problems. First, accuracy. Hitting a narrow dam wall from thousands of feet in wartime conditions was difficult enough. Second, even a direct strike against the upper structure might damage the crest without producing the deep structural failure needed to release the reservoir. An underwater attack seemed more promising. Explosive force behaves differently when it is trapped by water. Water does not compress easily, so an underwater detonation close to a wall can transmit a severe pressure wave into the structure. In principle, the reservoir could become part of the weapon. But German defenses had already closed the obvious route. Anti-torpedo nets hung in the water in front of the dams. A conventional torpedo could be caught before it reached the masonry. Detonating several dozen feet away was not the same as detonating against the wall. So the real question was not how to build a larger bomb. It was how to put a large explosive charge in the one place the defenses were designed to deny. Barnes Wallis, an aircraft designer and engineer at Vickers Armstrongs, attacked that problem from the physics outward. Wallis had spent years thinking about strategic targets and the way carefully chosen infrastructure could influence an industrial system. The dams interested him because their strength also contained a weakness. The water they held back was pressing against them continuously. If an explosion could create a serious fracture in the right place, the reservoir might enlarge the damage far beyond what the explosive could do by itself. That idea still left the delivery problem. A torpedo would meet the nets. A conventional bomb would be too inaccurate. A huge high-altitude weapon might strike somewhere near the dam, but near was not good enough for the effect Wallis wanted. His answer came from an old and almost childish motion, a stone skipping across a pond. If a body hits water at a shallow enough angle with enough horizontal speed, hydrodynamic lift can push it back into the air. It loses energy on each impact, but under the right conditions it can travel across the surface instead of immediately sinking. Wallis began with small experiments, then moved toward larger tests. The concept looked promising until another problem appeared. A skipping object that finally hits a vertical wall can rebound away from it. For this mission, that would be disastrous. The weapon could clear the nets, strike the dam, then bounce backward and sink too far from the masonry. The solution was backspin. Spin the cylinder backward before release, and its behavior changes. The rotation helps stabilize the path across the water. More importantly, when the weapon reaches the dam, the spin works against the tendency to rebound cleanly away. Instead of simply ricocheting back into the reservoir, the rotating cylinder is encouraged to remain close to the wall as it sinks. The concept eventually became Upkeep, the large cylindrical mine developed for the operation. It was an extraordinary object to hang beneath an aircraft, about 5 feet across, packed with several tons of explosive, and heavy enough that the Lancaster carrying it had to be specially modified. But the most important feature was not its shape. It was that Upkeep turned the aircraft into part of the weapon. A normal bomb is designed to tolerate some variation in release. Upkeep was not. Its path across the water depended on a narrow combination of height, speed, spin, and distance. The bomber had to deliver those conditions with a level of precision that did not belong to normal heavy bomber operations. That changed the problem completely. The engineers had found a way around the torpedo nets. Now someone had to fly the equation. The standard Lancaster was designed for a very different kind of war. It was a heavy bomber built to carry a large bomb load across long distances, normally at altitudes where terrain, trees, and telephone wires were far below the crew's immediate concern. For Operation Chastise, that aircraft had to be stripped and altered around a single weapon. The bomb bay doors were removed. Special arms held the Upkeep cylinder beneath the fuselage. A drive system spun the weapon backward before release. Weight had to be saved and defensive equipment was reduced. The aircraft that emerged from the conversion was still a Lancaster, but it had become a highly specialized low-level strike machine with almost no margin for improvisation. The same was true of the men chosen to fly it. In March 1943, a new unit was formed at RAF Scampton, 617 Squadron. Its commander was Wing Commander Guy Gibson, only 24 years old but already an unusually experienced operational pilot. The squadron drew crews from across Bomber Command, including men from Britain, Canada, Australia, and New Zealand. They were not told everything at once. Security around the weapon and target remained tight, but the flying requirements alone told them that this was not a normal bombing mission. They were ordered to practice at extremely low altitude, often at night. That meant learning to fly a 30-ton aircraft in a part of the sky where heavy bombers normally did not belong. Over land, the danger was obvious. Trees, church spires, ridges, and power lines arrived with almost no warning. At low level, the pilot could not simply correct a mistake with a gentle climb. Every correction cost speed, altitude, or surprise. The navigator also had less time. Instead of identifying a feature and planning minutes ahead, he might have seconds to recognize a road junction, railway line, canal, or bend in a river before it disappeared behind the aircraft. Over water, the danger became stranger. At night, calm water can erase depth perception. A dark reservoir under a dark sky offers almost no texture. There may be no reliable horizon, no visible ripples, no shadows, nothing that allows the eye to judge whether the aircraft is at 100 feet or 50. The Lancaster's normal barometric altimeter could not solve that problem. At high altitude, an error of several dozen feet was unimportant. At 60 feet, the same error could be fatal, and 60 feet was not an aesthetic choice. It was tied to the way the weapon met the water. Too high, and the impact angle could be wrong. Too low, and the bomb might not develop the required bounce, while the aircraft itself would be dangerously close to spray and blast effects. The mission therefore reached a paradox. The weapon demanded a height the crew could not reliably read from the instruments they normally used. The answer was not advanced radar. It was geometry and two lamps. Technicians mounted two downward-facing spotlights under the Lancaster at different angles. One beam pointed slightly forward, the other slightly aft. Their angles were calibrated so that when the aircraft was at the required release height, the two bright patches on the water met. From the cockpit, the system was almost absurdly simple. If the light spots were separated, the aircraft was not at the correct height. As the pilot adjusted the Lancaster, the spots moved. When they converged into one overlapping pattern, the crew had a direct visual cue that the bomber was where it needed to be. In effect, the aircraft carried its own ruler and projected it onto the reservoir. The solution was brilliant because it did not require the water to provide any natural reference. The crew created the reference themselves. It was also terrifying because the same lights that helped the navigator judge altitude could make a low-flying bomber easier to see from the ground. Height was only half the problem. The Upkeep mine also had to be released at the right distance from the dam. Standard high-altitude bomb sites were built around a different geometry. Their job was to predict the path of a bomb falling through thousands of feet of air. At 60 feet, flying almost directly at the target, the timing problem was compressed into seconds. Again, the answer was almost primitive. On the Möhne Dam, two towers on the crest provided known points. A simple triangular aiming device could use the apparent separation of those towers to tell the bomb aimer when the aircraft had reached the release point. Different accounts describe improvised forms of the device, but the principle was straightforward. When the towers matched the calibrated sight, distance had been converted into a visual angle. No electronic computer was needed. The most sophisticated part of the attack was a spinning multi-ton mine. The two most important pieces of targeting equipment were a pair of lights and a simple geometric sight. That contrast explains the mission better than any slogan about a wonder weapon. The technology worked because each complicated problem was reduced to something a human being could see in real time. Height became 2 circles of light, distance became 2 towers fitting a sight, speed became a needle the pilot had to hold steady. And every one of those signals had to agree at the same moment, while the bomber was moving more than 300 feet every second. Testing made clear how unforgiving that moment would be. Full-scale drops were conducted off the English coast, including at Reculver in Kent. Early tests showed how violently the water could punish a weapon that arrived at the wrong angle. Casings broke, experimental forms failed, spray and debris demonstrated what an error would mean for an aircraft following close behind its own bomb. The trials also forced the weapon and the flying technique to evolve together. The engineers could not design Upkeep in isolation and then hand it to the squadron. Every adjustment to the bomb affected the release. Every practical difficulty in the cockpit fed back into the delivery system. That is why 617 Squadron's training mattered as much as Wallis's calculations. The crews practiced low-level navigation until roads and rivers stopped being scenery and became survival markers. They rehearsed approaches to reservoirs and dams in Britain. They learned how slowly a heavy aircraft responds when it is already close to the ground, and how much discipline it takes not to pull up merely because every instinct says to gain altitude. They also learned something more uncomfortable. The final attack run could not be flown defensively. To release the weapon correctly, the pilot needed a stable platform. He could not weave wildly to avoid every tracer. He could not change height each time the ground fire looked close. In the last seconds, survival depended on doing the opposite of what fear demanded. He had to hold the Lancaster steady. By the evening of May 16th, training ended and secrecy gave way to purpose. 19 specially modified Lancasters were assigned to the operation. The raid was organized in waves, with the main force aimed first at the Möhne, and then the Eder, while other aircraft were directed toward the Sorpe and alternate targets. The crews now knew what they were carrying and what the dams meant. They also knew the route would be dangerous long before they reached them. The operation depended on surprise. Flying in a normal bomber stream at normal bomber altitude would expose the force to the German night fighter and radar system, so the Lancasters went low, very low. Across the North Sea and into occupied Europe, they flew close to the surface, then close to the land. At such heights, radar detection could become more difficult, but the landscape itself became an enemy. A line of trees could fill the windscreen in seconds. A ridge that looked harmless on a map could force a violent climb. High-voltage cables were nearly invisible until the aircraft was almost on top of them. Navigation errors that might cost a few minutes at altitude could become fatal at treetop height. The squadron began losing aircraft before the dams came into view. One Lancaster struck power lines and crashed, killing its crew. Another aircraft hit the sea during an evasive maneuver and lost its weapon, forcing it to turn back. Other crews suffered damage or navigational problems that prevented them from reaching the attack as planned. This was the first hard correction to the clean mathematics of the mission. The biggest danger was not yet the dam defense. It was the route required to get there. Inside each surviving aircraft, the workload was relentless. The pilot had to keep the bomber low without clipping terrain. The navigator had to find tiny features in darkness while the ground passed underneath at high speed. The flight engineer managed the 4 engines and fuel. The wireless operator listened without breaking the discipline of radio silence. Gunners watched for threats that could appear almost level with them. And beneath the fuselage, Upkeep hung in the slipstream, waiting for the moment when its drive motor would spin the cylinder backward. As the force moved deeper into Germany, the low-level tactic produced a strange inversion of the normal air war. German defenses had been built largely around detecting and attacking bombers above the landscape. Heavy anti-aircraft guns were most effective against aircraft at altitude. Night fighters needed warning, position, and time to intercept. A Lancaster racing below the radar horizon could avoid some of that system. But when it entered the narrow approach to a dam, the advantage disappeared. The aircraft had to line up with a fixed structure. It had to hold a predictable course. It had to fly at a predetermined height and speed, and it had to illuminate the water beneath itself. At that point, every feature that made the weapon accurate also made the bomber easier to shoot at. The Möhne reservoir was the first great test. The dam presented a broad, comparatively direct approach across the water. That made it suitable for the bouncing attack, but it was defended by light anti-aircraft weapons positioned to cover the approaches in the crest. Gibson went first. That decision mattered tactically and psychologically. Nobody in the squadron yet knew what a full attack run would look like under actual fire. Somebody had to convert the training pattern into combat while the others watched. Gibson brought the Lancaster down toward the reservoir. The spotlights went on. Two pools of light raced over the black surface. The navigator called corrections. A little lower, hold it, a little higher. The pilot worked the controls in tiny movements, trying to keep a large aircraft balanced at a height that left almost no visual margin. The speed stabilized. Ahead, the dam towers grew larger. The gunners on and around the dam opened fire. Tracer crossed the water. At low altitude, the rounds did not seem to rise from the ground toward an aircraft in the sky. They came almost straight at the cockpit, bright lines moving across the same horizontal plane as the Lancaster. The bomb aimer watched the towers in the sight. The release point arrived. Upkeep dropped. For a fraction of a second, the huge cylinder simply fell. Then it struck the surface and vanished inside a wall of spray. It came out of the spray moving forward. The bomb hit again, bounced again, and crossed the defended water toward the dam. Gibson's attack did not breach the structure. The detonation threw water and spray high above the reservoir, but the Möhne remained standing. That failure was important for reasons beyond the immediate result. The basic system had survived contact with combat. A Lancaster had reached the correct attack profile, released the spinning weapon under fire, and produced an underwater explosion near the target. The problem was now narrower. The dam still had to be broken. Flight Lieutenant John Hopgood was next. By then, the defenders had a better understanding of the approach. His Lancaster came in along essentially the same line, and concentrated fire struck the aircraft. The damage was severe. A wing caught fire. The bomber was already in trouble before it reached the release point. Yet the crew continued the run. At this altitude, abandoning the attack did not guarantee survival. Pulling away while damaged could expose the aircraft to more fire or cause a stall close to the water. The only useful path in front of them was still the one they had practiced. Hopgood's weapon was released, but the attack did not produce the required hit. The damaged Lancaster climbed away burning and crashed soon afterward. Some crew members escaped, but most were killed. For the aircraft waiting to attack, the message was brutal. The problem was no longer theoretical precision. It was precision after watching the bomber ahead of you burn. That distinction would define the rest of the night. The third attacker was Flight Lieutenant McMartin. Gibson had already dropped his own weapon, so he could do something the attacking bomber could not. He could maneuver without worrying about release geometry. During subsequent runs, he flew near the attack path in an effort to draw some of the defensive fire away from the aircraft carrying bombs. It was a simple decision with an ugly logic. A bomber that had already used its weapon could become a decoy for one that had not. Martin came down onto the water. His crew brought the two light spots together. The bomb aimer watched the dam towers grow through the sight. The German guns continued firing. Then the weapon went. This time the sequence looked close to what Wallis and the crews had spent weeks trying to create. The cylinder struck the reservoir, skipped across the surface, cleared the defenses, reached the dam, and sank close to the masonry before detonating. A huge column of water rose behind the wall. When it fell, the dam was damaged but still intact. This was the moment when the operation could have begun to look like a failure even though the weapon was functioning. A successful delivery was not the same as a successful breach. The Möhne was massive. Its strength did not vanish because a new weapon had reached it. The mine still had to create enough damage at the right place for the reservoir pressure to exploit. Another crew had to make the same run. Squadron leader Henry Dingy Young attacked next. Again, a Lancaster crossed the water at extremely low altitude. Again, the crew held the release conditions while fire came from the dam defenses. Again, Upkeep reached the wall and detonated underwater. The dam still stood. By then, the surviving crews circling the reservoir could see that the problem was cumulative. Each attack might be weakening the structure, but there was no useful way to measure that damage from the cockpit. They could see spray. They could see water pouring over sections of the crest. They could see smoke and tracer. They could not see what was happening deep inside the masonry. Flight Lieutenant David Maltby made the next attack. The air over the reservoir was now worse than it had been for Gibson. Previous detonations had disturbed the water and filled the approach with smoke, spray, and debris. The defenses were fully awake. The crews had already seen aircraft hit. Still, the procedure did not change. The lights had to meet. The speed had to hold. The towers had to reach the correct angle. The release had to happen. Maltby's weapon bounced toward the dam and detonated beneath the surface near the wall. For a moment, the result looked familiar. Water rising, spray obscuring the structure. Then the shape of the dam changed. A section of the central masonry began to fail. The reservoir found the weakness and forced itself through. The breach widened rapidly under a pressure that had been building behind the wall long before the Lancasters arrived. The weapon had not blown an empty wall apart by explosive force alone. It had opened a path for the stored energy of the water. That was the mechanism Wallis had been trying to reach from the beginning. From the aircraft above the reservoir, the scene was immense. Water accelerated through the opening and dropped into the valley below. Roads, power installations, bridges, fields, and settlements lay in the path of a flood that had no ability to distinguish military infrastructure from human life. The squadron had achieved its first major objective. It was not finished. The remaining aircraft now had to turn toward the Eder Dam. The Eder presented almost the opposite tactical problem from the Möhne. It was less heavily defended, but its geography made the attack much harder. The dam sat among steep hills. The approach was short and confined. A Lancaster could not simply settle onto a long, straight run across open water. The pilot had to descend into the valley, line up, stabilize height and speed, release, and then climb away before terrain closed the route. The aircraft was large. The valley was not. Crews made repeated approaches and broke them off when the geometry was wrong. That detail is important because it reveals what the bombing system actually demanded. Courage alone could not substitute for the release conditions. A pilot could be completely willing to attack and still have to abandon a run because the aircraft was too high, too fast, too far offline, or too unstable. The weapon did not reward bravery. It rewarded a very specific kind of discipline. The willingness to admit that a bad approach was useless and try again, even while fuel disappeared, and the night continued to close around the aircraft. One of the successful Eder attacks was made by Flight Lieutenant Les Knight. After earlier attempts by other crews had failed to produce a breach, Knight brought his Lancaster through the difficult approach and released his weapon. The mine reached the dam and detonated close enough for the structure to fail. The Eder was breached. Again, water became the final destructive force, pouring through the opening and down the valley. Two great masonry dams had now been broken in one night, but the third principal target would expose the boundary of Wallis's idea. The Sorpe was not built like the Möhne or Eder. It was primarily an earth embankment dam, a broad mass of material rather than a near-vertical masonry wall, presenting the same underwater target geometry. The bounce and sink method had been designed around a particular relationship, a weapon crossing water, reaching a steep wall, sinking close to it, then detonating where water pressure could drive shock into the structure. At the Sorpe, that relationship did not exist in the same form. The terrain also made a normal perpendicular run difficult. Crews attacked along the length of the dam, trying to place weapons on or near the crest, rather than using the classic bouncing approach against a vertical face. The attacks damaged the Sorpe but did not breach it. That failure was not a footnote. It was proof that Upkeep was never a universal answer to dams. It was a highly specialized solution to a highly specific target shape. The same narrow conditions that made the weapon remarkable also limited where it could work. The crews still had to get home. By then the Lancasters were lighter without their weapons, but they were not necessarily safer. Fuel had been consumed by low-level flying, repeated approaches, and evasive maneuvers. Some aircraft had been damaged by flak. Every crew was exhausted from hours of flying in a regime that demanded constant attention. The return route required the same basic bargain as the approach. Climb, and the aircraft became easier for radar, searchlights, fighters, and heavy anti-aircraft defenses to find. Stay low, and the bomber remained close to the obstacles that had already destroyed aircraft on the way in. So the crews went back across occupied territory at low altitude. The landscape that had been difficult to read before the attack was no easier afterward. Power lines were still invisible until close. Trees and ridges were still waiting. German defenses were now alert to the presence of low-flying heavy bombers, and tired pilots were trying to make precise control inputs after spending hours under physical and psychological stress. The raid continued to take aircraft on the return journey. By the time the surviving Lancasters crossed back toward England, 8 of the 19 aircraft dispatched on the operation had been lost. 53 airmen were killed, and 3 became prisoners of war. Those numbers cut directly against the clean image that quickly grew around the raid. Operation Chastise would become one of the most famous Royal Air Force operations of the Second World War. The sight of bombs bouncing across water and dams collapsing under enormous floods was visually unforgettable. It offered the British public a story of ingenuity, nerve, and spectacular success at a time when the war still demanded enormous sacrifice. But the crews who returned to Scampton did not come back to a simple victory. Empty dispersal areas showed where aircraft should have been. Men who had eaten, trained, and flown together were missing. And below the breached dams, The consequences extended far beyond the industrial targets the planners had discussed. Floodwater moved through the valleys with destructive force, damaging power stations, roads, bridges, factories, farmland, and homes. Civilians were killed. Foreign forced laborers and prisoners were also caught in the flooding, including people who had little or no ability to escape from camps and controlled worksites. The water did not separate the German war economy from the human beings living inside it. That fact belongs inside the story, because it changes the meaning of the engineering. The same mechanism that made the weapon effective against infrastructure made its effects impossible to contain once a dam failed. Wallis's concept depended on the reservoir releasing its stored mass through a breach. The tactical success and the civilian disaster were therefore not separate physical events. They came from the same chain of cause and effect. This does not erase the military purpose of the operation. The Ruhr mattered to German armaments production. The dams were legitimate strategic targets within the logic of wartime bombing as Britain understood it, but the raid's human consequences resist the neat idea of an engineering puzzle solved cleanly. A breached dam is not a factory machine that simply stops. It changes a landscape. The strategic result was also more complicated than the dramatic images suggested. The damage created a serious emergency. Water supplies and power were disrupted. Transport and industrial facilities in the affected valleys suffered. German authorities had to redirect manpower and resources toward repair, including labor that might otherwise have been used on other defensive projects. For a period, the raid imposed real costs, but it did not permanently paralyze the Ruhr. The German state responded quickly and brutally. Repair work was organized on a large scale using forced labor as well as construction units. Temporary systems restored essential functions. The breached dams were repaired far faster than British planners had hoped, and the industrial region recovered much of its capacity within months. That outcome matters because it prevents the story from ending with the visual climax at the mowing. The raid succeeded tactically in a way that had seemed close to impossible. 2 major dams were breached. A new weapon was delivered under extreme conditions. German resources were diverted. The operation became a powerful psychological and propaganda success for Britain. But the larger strategic promise was only partly fulfilled. There was no permanent industrial collapse. The Sorpe remained standing. The weapon was so specialized that its future uses were limited, and the cost to 6 and 17 Squadron was devastating. That combination is what makes Operation Chastise more interesting than a story about a clever bomb. It shows how military innovation actually behaves. A new idea can solve one problem while creating another. A weapon can defeat a defense and still depend on conditions so narrow that only a small number of crews can use it. A spectacular physical result can produce less strategic effect than expected. A mission can be both a genuine feat of engineering and a human catastrophe. The bouncing bomb itself has become the symbol, but the symbol can hide the system that made it work. Upkeep did not simply leave an aircraft and perform magic. Its success depended on a chain of people and decisions. Wallis had to identify the physical relationship between explosive force, water, and masonry. Engineers had to turn a concept into a full-size weapon that could survive release and impact. Avro had to modify Lancasters to carry and spin it. Test crews had to expose failures that drawings could not predict. 617 Squadron had to learn a new form of low-level navigation. Navigators and bomb aimers had to convert geometry into visual cues that could be used in darkness. Pilots had to resist the instinct to climb or dodge during the exact seconds when the aircraft needed to remain stable, and the entire chain could still fail if one variable moved outside the narrow window. That is why the raid cannot be reduced to a single inventor or a single moment of impact. The weapon was the visible object. The real achievement was integration. To understand that integration, it helps to return to the final seconds of an attack run and strip away the legend. There was no single instrument telling the crew that the solution was correct. The pilot had airspeed and the physical feel of the aircraft. The navigator had the converging lights on the water. The bomb aimer had the dam towers and the calibrated sight. The flight engineer had engines that had to deliver steady power while the Lancaster flew in dense air close to the surface. The gunners had the defenses. Each man saw only part of the problem. The release happened only when those separate pieces briefly agreed. That is a very different kind of precision from pressing a button after a computer has solved the geometry. It was distributed precision. The aircraft itself became a moving measuring device, and the crew became the processing system. One person called height. Another controlled attitude. Another judged range. Another kept the power stable. If a correction came late, everyone downstream inherited the error. At high altitude, seconds can feel long. On the reservoir, seconds were distance. At roughly 200 miles an hour, A hesitation could move the aircraft hundreds of feet. A small climb changed the bomb's impact angle. A small change in speed changed the spacing of the bounces. A late release changed where the cylinder met the dam. The men were not trying to be generally accurate. They were trying to make several errors become zero at the same instant. That requirement explains why the mission was so physically exhausting. A pilot could not simply aim at the dam and fly toward it. He had to keep the Lancaster inside an invisible corridor that existed only as numbers in the briefing and light patterns on the water. The German gunners understood none of the mathematics, but they did not need to. Their task was to force the attacking aircraft out of that corridor. A burst of tracer that made a pilot climb was enough. A hit that damaged an engine was enough. A shell that forced a bank at the wrong moment was enough. The defenders did not have to destroy every Lancaster. They only had to make precision impossible. That is why Gibson's decision to return near later attack runs mattered. The aim was not heroism for its own sake. If his aircraft could attract even part of the defensive attention for a few seconds, it might reduce the pressure on the crew that still had to hold the exact line. The raid therefore became a contest over stability. The weapon needed stability in height, speed, spin, and release point. The terrain attacked stability before the target. The defenses attacked stability over the reservoir. Fear attacked stability inside the cockpit. And the crews had to preserve it long enough for a steel cylinder to leave the aircraft in the right place. This also explains why the simplest tools became so important. The converging spotlights were not crude substitutes for better technology. For this specific problem, they were better than a conventional altimeter because they measured the thing the crew actually needed, distance from the surface at the point of attack. The geometric sight did something similar. It did not attempt to model the entire flight of the weapon. It turned a fixed architectural feature on the dam into a range cue that a bomb aimer could use instantly. Both solutions removed calculation from the final seconds. That was the hidden sophistication of the system. Complex thinking had been done on the ground so the crew could make simple decisions in the air. 2 lights merge. Height is right. 2 towers fit the sight. Range is right. Hold the speed. Release. In a laboratory, simplicity can look unsophisticated. In combat, simplicity can be what remains usable after everything becomes violent. Wallis's work is often remembered because the image of a bomb bouncing across water is so strange. But the more revealing engineering may be the work that surrounded the bomb. Identifying what the crew could realistically observe, then designing the attack procedure around those observations. The operation did not remove human limitation, it designed around it, and even then, the limits remained severe. The night route cost aircraft before the target. Defensive fire destroyed or damaged others. Repeated approaches at the Eder consumed time and fuel. The Sorpe demonstrated that the weapon's geometry could not simply be transferred to a different kind of dam. The floods caused destruction far beyond military machinery. Repairs reduced the long-term industrial effect. Every stage contained a boundary. That is why the most accurate legacy of the raid is neither triumph nor futility. It is a demonstration of what happens when a narrow engineering idea is pushed all the way through a real military system. Some parts work better than expected. Some fail. Some succeed at a cost that changes the meaning of success. And some produce consequences that the original calculation cannot contain. On the morning of May 17th, Barnes Wallis had evidence that the concept could do what had once seemed physically absurd. A heavy explosive could be made to cross water, defeat anti-torpedo defenses, reach a dam, and help produce a catastrophic breach. The crews of 617 Squadron had proved something equally important. A large bomber could be trained to deliver that weapon under conditions for which it had never been designed. But the empty places at Scampton proved the other half of the equation. Making the impossible possible did not make it safe. The men who died were not a side note to an engineering success. Their losses were part of the price of a system that required aircraft to fly close to terrain, close to water, and directly through defensive fire. The civilians and forced laborers killed downstream were not abstract collateral to a dramatic breach. They were human consequences of using a reservoir as stored destructive energy. And the repaired dams were evidence that even spectacular tactical success can shrink when measured against a larger war economy capable of emergency recovery. There is another reason the raid still attracts attention. It compresses several different meanings of success into one night, and those meanings do not line up neatly. At the level of engineering, success meant proving that a spinning cylindrical mine could be delivered across water and made to detonate close to a dam wall. At the level of flying, success meant getting a modified heavy bomber to the release point with the required height, speed, and alignment. At the tactical level, success meant creating a breach, At the operational level, success meant disrupting water, power, transport, and industrial activity across part of the Ruhr. At the strategic level, the question was larger. Would those disruptions last long enough and spread far enough to materially weaken Germany's ability to continue the war? The raid answered the first 4 questions more strongly than the 5th. That difference matters because dramatic military operations are often judged by their most visible moment. A dam collapses, a flood races through a valley, a photograph shows a gap in a structure that had seemed permanent. Those images make the result feel final. War rarely works that way. Systems recover, engineers repair, labor is redirected, production is rerouted, temporary solutions buy time. The enemy adapts. The larger the industrial system, the more important recovery capacity becomes. So the breached dams were both proof and warning. They proved that a defended structure could be attacked through an unexpected physical mechanism. They also warned that destroying a critical node is not the same as permanently disabling the system around it. That distinction keeps the raid grounded. It allows the courage of the crews and the originality of the engineering to remain extraordinary without requiring the operation to become a war-winning miracle. The same distinction also clarifies the role of 617 Squadron. The crews were not simply brave men carrying a clever device. They were the final control surface in an experimental system. Their judgment corrected what instruments could not measure quickly enough, and their discipline held together variables that the weapon could not control for itself. That is why the operation was so difficult to reproduce at scale. The aircraft could be modified, more mines could be manufactured, but the attack profile demanded crews trained for a rare combination of navigation, formation discipline, low-level handling, and precise release under direct fire. The human skill was not an accessory to the technology. It was one of its essential components. Those truths can exist together. Operation Chastise was a remarkable act of wartime engineering. It was an extraordinary display of aircrew discipline. It was costly, it was destructive beyond the intended industrial system, and its strategic effect was significant but temporary. Remove any one of those facts and the story becomes easier. Keep them together and the story becomes more useful. Because the deepest contradiction of the raid was never simply that a bomb could bounce. It was that an idea elegant enough to fit on a drawing board required human beings to enter an environment where elegance disappeared. The laboratory could define the right height. The test range could define the right speed. Geometry could define the right distance. But none of those things could make a burning aircraft fly straight, or make a navigator see through smoke, or give a pilot extra altitude after a mistake at treetop level. In the Ruhr valleys, every clean number had to be carried by a tired human body. And for a few decisive seconds over black water, the entire design depended on those bodies refusing to move outside the numbers. 2 beams of light came together on the reservoir. A bomber held 60 feet where no heavy bomber was meant to fly, and only then did the mathematics become real.